typed programmatic interface to contracts on the blockchain at APLAS. This work is done in collaboration with my postdoc, Doan, who is unfortunately stuck in her home country, so I'm giving the talk, although I obviously can't attend in person either. So here's an overview of my talk, but let's start right away by giving you some context. So the title mentions blockchain. So what's the blockchain? It's an immutable list of digital records, also called ledger or append-only log. So this is maintained by a peer-to-peer network, which means it's open and it's replicated. So it implements practical distributed consensus with the consequence that the results are unforgeable if more than 50% of the participants in the network are honest. And it's the basis for the first successful implementation of a cryptocurrency, namely Bitcoin. The title also mentions contracts, which are mostly called smart contracts. This is really about programs that are stored on the blockchain along with their data. So each contract also owns some crypto coins, because each blockchain also is associated with a cryptocurrency, and executing a contract means that we are talking about replicated deterministic computation. So we have some sort of fail-safe global computer which is unforgeable and unforgiving. Yeah? And the typical mention here is Lawrence Lessig's moniker, code is law, meaning code will execute no matter what happens to the rest of the world. Right, so all that actually comes with a cost. I shouldn't deny that. So storing anything, programs or data on the blockchain costs some fee, some crypto coins, and also performing the computation costs crypto coins. Right, now, there's a lot of things that contracts can do, but there's also a couple of things that contracts cannot or maybe should not do. One example is randomness or external triggers. So you're executing deterministically. So how should you be random, or what should trigger you? Also timers. Another thing is computation-intensive algorithms that operate on large data. That's just too costly to run on the blockchain. Also, having proprietary algorithms on the blockchain is not such a good idea, because everyone can look inside. So here we shall focus actually on the first three items, namely on interoperation. So there are a couple of use cases here. For example, you could have some sort of event-driven interoperation where you automatically file a claim if a flight is delayed, or you sell crypto coins if the exchange rate reaches a threshold, or maybe an auction finishes after 48 hours or something. Or you could also talk about automatizing processes. For example, you might want to optimize a transaction by running it either for the best price, at the best price, or at the best possible throughput. You might also implement a strategy for bidding an auction, and that's actually an example that we have in the paper. Or you could create a Nifty. All right, so this work happens in the context of the Coke project, which is about orchestration of contracts. All that happens on Tezos, which is a third generation blockchain. So our goal is here to provide tools for writing oracles and automatic processes in OCaml, which happens to be the implementation language of Tezos. So in this work, we are concentrating on writing presenting a type-safe API to Tezos contracts. So this is actually modeled in a slightly non-standard way as a language extension, and we have an implementation that comes with it, and we've proved some of the meta theory of our API. Let's start with a look at the practical side. Let's have a look at the API. Well, of course, there is a way to programmatically access any blockchain, and the same is true for Tezos. So what Tezos does is it provides a command line interface and an RPC API and that allows you to obtain various information, actually to perform any operation on the blockchain. And here these are just some examples. Now, the Tezos provides you with a OCaml library, which is essentially a thin wrapper with some nice extra functionality around the RPC API. However, that comes with some drawbacks. So it's a large API. There's some lack of abstraction, and you'll see what I mean in a minute. And also, large parts of the interface are based on strings. In particular, the parts that is where it gets to exchanging data between your calling program and your contract on the blockchain. All right. So let's be concrete, and here I'm presenting you a simple counter contract in Michelson. Michelson is the smart contract language of Tezos. So the input of a Michelson contract is the parameter and the current storage. Yeah, and both are specified by this header of a Michelson contract. So in this case, the storage holds a natural number. Here these percent things are just annotations which give it a human readable name, a more descriptive name. And the parameter is a sum type, and each of the summons has been marked up with its own name. And this is Tezos' way of providing different entry points to a contract. Yeah, so depending on how you choose your parameter, in which of those three summons your parameter lies, this makes the choice between different entry points. So in our case, the entry points are up for incrementing the counter, down for decrementing it, and default for resetting the counter. Oh, and I just see that some parts are cut off my nice slide, which is a pity. All right, sorry. So concretely, what are we doing? A contract is typically, after it's deployed, it's given by a hash. Yeah, so then our library provides a function make contract from hash that takes such a counter hash. Along with that, it takes a representation of the type of the parameter and a representation of the type of the storage. Now what happens at runtime is, well, our API checks, does this contract exist? Does it have a parameter of the type specified? Does it have storage of the type specified? The nice thing is, well, it happens at runtime, that's maybe not so nice, but the nice thing is it happens at no cost. So there is no blockchain transaction needed in order to verify these types. So once that is verified, we actually obtain a typed handle counter where the parameter is mapped into a corresponding OCaml type, and also the storage type is mapped into a suitable OCaml type. Right. So how can we work with that? So here is a very simple thing. There is a nicer, better motivated example in the proceedings. So here let's just try to keep the counter close to a target. So here we are invoking some part of the API, get storage, obtains the current storage value of the counter contract. And since counter is a typed handle, we know, well, get storage returns us a value of a suitable OCaml type that represents the current storage. And these observer functions always succeed, and we can just work with them. Then there are other functions here like call contract. So call contract is also fully typed. Yeah, it takes the counter handle and then it knows, okay, now I need to take something of the parameter type mapped to OCaml again. And in this case, left unit means we are selecting the up entry point, right and left unit means we are selecting the down entry point. And so the different thing is now these contract calls may fail, maybe because we're not paying enough, maybe there is some timeout in the system, or they can also be some sort of programmed failures. Programmed failures are captured, I mean, all these leads to an exception, and programmed failures are captured here with a suitable fail with exception, and then we just recursively invoke the polling function again. Otherwise, if we succeeded, then we sleep for a while so as not to burn too many resources and try again. All right. So much for the practical side. Let's now turn to the formal system that is presented in the paper. So, so the formal system encompasses the interaction between the blockchain and the program in full. That is, we've got a global configuration that is comprised of the state of the blockchain and then many nodes that work independently, concurrently. Each local node, again, contains some state about the accounts that live at that node, and then it contains a number of threads, any number of threads that again run concurrently. Now then we've got deterministic evaluation of the expressions in each single thread, and these expressions are taken from lambda calculus with domain-specific primitives which perform operations on the blockchain. Then on the higher levels we've got non-deterministic reduction, so reduction on the local node. Well, non-deterministically selects one of the threads to make progress, and also on the global configuration we also non-deterministically select a node and then perform some action in that node. Right, let's have a look at the type system. So the type system, the type discipline that we are using here, is based on simple types. This is because, well, the Michelson language that's powering the Tezos blockchain is also based on simple types. On top of that, we have domain-specific types, which are mostly inspired from Michelson. For example, we have a type contract of T and U, and this is a contract handle with parameter type T and storage type U. This is actually more concrete than in Michelson, and you'll see why on the next slide. Another workhorse here is typecast. So we have a notion of compatible types. We could be using subtyping, but we want to embed into OCaml, which doesn't have subtyping. So we stay faithful to that embedding and just define a notion of types which is called compatible. And then we have a cast operation, and the cast operation allows us to transform values from one compatible type to another, possibly. If we go the up direction, like PUH is the type of a public hash, so that's certainly an address. PUK is a public key type, that's certainly an address as well. And then a contract handle that's also at runtime represented by a public key hash. So a contract is obviously convertible to a public hash, but we're forgetting in that transition that it's actually a contract. So downcast, going back from an address to a public hash or from a public hash to a contract requires a runtime check. And in the latter case, from public hash to a type contract handle, this actually requires a query to the blockchain verifying that, well, this is a contract, what we discussed before with the handle. That's happening in the cast from public hash to contract of T and U. All right, so here's some typing rules. I would just like to highlight two elements here. So I'm showing the typing rules for two blockchain operations, transfer and originate. Both return an operation handle, and an operation, and both of these operations are non-blocking. So they're immediately returning the handle. So now what can we do with the handle? Either we can non-blockingly ask for its status, or if the handle is suitably typed, then we can try to convert it into a contract. And we see that it's suitable type if the types here are sufficiently informative. Now, this is a blocking operation, obviously. We have various technical results. So we prove invariance of the blockchain semantics, we prove meta theory, typing preservation, and progress. Progress happens because blockchain operations actually are able to time out. To conclude, the objective of our work is automatizing processes on the blockchain. We do so in a type-safe way. We've presented a non-deterministic abstract execution model of the Tezos blockchains, and we've got a simple type system with domain-specific extensions ready to go.